Hello again, Martin. Do you hear me?
Yes. Hi.
I did not realize that that the fact that I closed the session disabled people to ask questions. Sorry about that.
Yeah, no problem. I can just say at the very beginning of the next session that they can pose the questions if they have any again in the chat, and then I can try to react on that.
Mm-hmm. Yeah.
Can you again try to make me co-host?
Oh yeah, sure. Where are you? Yes, it should be good.
Okay, perfect. I can also.
And I have the possibility to create the breakout rooms, and there is an option to either let people choose in which room they want to go or to assign automatically.
I think we can do it automatically. Then it's just a random choice, and then it is as it is.
Yeah. Okay. Sure.
Yeah.
It's easier.
Okay.
Easier.
Good. I will mute myself and turn off the video for some more minutes, and we'll be back in 10 minutes then before the meeting. Okay?
Yeah. Sure. No problem.
See you.
See you.
From my side, I will share my screen. Maybe before I do so I can maybe say also a bit regarding the organization of the exercise class at the end of this lecture. Okay, and then you know maybe a bit what's going on. Okay, but let's start where we stopped. You should again see my slides, and you should now see it also in full screen mode again. And if I remember correctly, this was the slide that I stopped on. So this was the, well, you have to make a compromise slide. So of course you can get as close to any non-linearity with such a piecewise linearization as you like or as you wish. But of course, the more accurate your model, your approximation will be, the harder it will be to solve the underlying mixed integer linear program, because the number of binary variables required will, of course, be larger. Okay, and there's a linear relationship. It's 1-to-1. Okay. So, by the way, these two methods that I now showed you this is not a comprehensive list. So in the literature, there are very, very many other methods that do kind of the same. That is modeling piecewise linear functions. So for instance, there's the multiple choice method. There are variants of the convex combination method. And there is, for instance, the logarithmic model. I guess this was published by Juan Pablo Vielma and co-authors. Maybe I can say a bit about this logarithmic model. So right now, we always used more or less exactly the number of intervals as binary variables to model these piecewise linear functions. And already from a information theory standpoint, it's clear that it should be doable with only logarithmically many. Okay, so this is what's at the core of the logarithmic model. So from a theoretical standpoint, maybe this is the most efficient one because it requires the minimum amount of binary variables. But in my experience, the incremental method is something that the solvers can deal very well with. At least this is my experience on the problems that I solved up to now with these things. But anyway, it's always good to know some more possibilities so that if you have a hard problem that needs to be solved, that you can maybe try different things in the end. Good. So I want to briefly come back to this separability issue. I mean, in the beginning, I said that we just make the assumption that the nonlinear function that we want to linearize is separable so that we can just do everything in 1D. Yeah. And of course, this is not always the case. Not all functions are separable, but some are at, or at least after some reformulations. Okay. So for instance, if you take a look here at this bilinearity between the variables x1 and x2, you can write this down as a separable model by introducing these two new variables, y1 and y2, that are given as this here. Okay. I mean, you can just plug it in and you see that it works. It's not that complicated. But what you also see is, I mean, you have to pay a price here because you introduce some other non-linearity that you have to deal with in your piecewise linearization. So it's again a compromise. Yeah? Another very well-known strategy, if you have, for instance, bilinearities, is to just take the logarithm. Yeah, of course, this gives you in the transformed world separable formulation, but again, you have other non-linearities that might have an ugly behavior, for instance, here close to zero. So what you see here is this only works if they are strictly positive, which you normally not have in an optimization model because you only have non-strict inequalities. So there are possibilities, but you have to check whether they are really appropriate for what you are going to do. Okay. Yeah, that's more or less what I said. Maybe some further topics in this linearization community. Of course, there are also other questions that I did not tackle. So for instance, the question, what are the breakpoints that you should choose? Okay, so the naive way is to just take an equidistant discretization of your interval that you're considering, but it does not mean that this is the best possible choice of breakpoints. Yeah, and I mean, if you want to do this really properly, then this opens the door to the mathematical theory of approximation theory. The best choice of these breakpoints can themselves be considered optimization problems. So there's a lot more to do if you want to dive into the details there. And of course, what I now avoided kind of is that there is an entire theory of multivariate linearizations as well. So there is the convex combination method. There is a incremental method also in d dimensions, or at least in 2 or in 3 dimensions. But in my experience, whenever you are able to use this separability, do it, because in 1D, it's rather easy to understand, and it's also very easy to implement usually. And this is at least this last bullet point, the easy to implement bullet point, is for sure not true for the multidimensional cases. Okay, good. You can also consider piecewise linear relaxations instead of approximations. This is what I showed you at the very beginning when I showed you the figure of the sine function. I did not yet discuss this in detail because this will also be one of the core topics of the general non-convex MINLP techniques that I'm going to discuss with you now. Okay, so this is the last bigger section, and here we are going to discuss what the state-of-the-art general purpose techniques for non-convex MINLPs are. Okay, so the question first of all is, what's the challenge anyway? So the problem is that if you consider again such a MINLP, that you have a non-convex MINLP according to the definition that I gave you this morning, if f or one of the component functions Cj of the constraint vector C is non-convex. And then you have the fact that even the problem that you get after relaxing the integrality constraints is a non-convex optimization problem. You remember this was the definition of an MINLP being non-convex. And then you have the issue that you have to solve these problems, the relaxations, to global optimality to get valid bounds. For instance, if you want to apply a technique like nonlinear branch and bound. And this is in general an NP-hard optimization problem as well. And this is why we have to deal here with a very hard problem, and which is why we have to discuss some other techniques as well. Okay, so this is what we discussed in the last section. Yeah, you already know an approach, the piecewise linear approximation approach. So since this is not that far away, I think I can go over this a bit more quickly. But what you can also consider is to apply branch and bound directly. And I have a very simple figure here that I will use to explain what you have to do if you want to have a branch and bound on non-convexities. So think about two continuous variables, x1 and x2. And you have this function here like f of x1 and is x2. So the graph of this function, this curve, this black curve here, this is the feasible set. And of course, since it's nonlinear, and if we are talking about an inequality constraint, this directly gives you a non-convex set. So we are also given bounds on the argument of the function. So we are given bounds on x1. So we have L here and U here as the lower and the upper bound for the argument. And what you usually do then in branch and bound for non-convex optimization problems, you try to figure out overestimators and underestimators for your feasible set, which is here the graph of your non-convex function, so that the graph itself is contained in the resulting feasible set that you obtain by these over and underestimators. So in this figure here, I chose a polyhedral approximation or a polyhedral relaxation. So I just chose this inequality constraint so that the feasible set is below this upper green curve and it's above the lower green curve. And you see it's a relaxation because the graph of the function is contained. So what you now can do is, since this feasible set is a relaxation, you can solve your original optimization problem, not over the non-convex graph here of the function, but over the convex relaxation. And since it's a relaxation, you get a lower bound. Okay, so this is doable, but you have a problem. And this is that this green feasible set that you obtain is usually much larger than your actual feasible set. Okay, so if you solve this problem over the convex relaxation of your non-convexity, you will more or less for sure not get a feasible point. For instance, you might get this point, which is the red one here. And then you have to see, okay, what shall I do? And now we have to branch in a different way compared to how we did it before. Before, we always branched on integer variables. We had a fractional integer variable, and then we chose one of those, and we branched on one of those. And this gave us two subproblems. And we know that the point before, the fractional one, is excluded from the feasible set. So the question is now, how do you do this with continuous variables? And this is what's called spatial branching. So we now have to branch on continuous variables, and this is spatial branching. So what this means is that you now have to take your arguments set here, the interval LU, and you kind of have to split it such that you generate two new subproblems as before, so that the old point is excluded, and that hopefully the feasible sets of the two new generated subproblems will be closer to what you want to approximate or relax here, which means that you will get better lower bounds in the two subproblems because the relaxation is getting tighter. So one possibility to do this here would be to just split this interval here at the red, at the blue line, so at x1 equals 0, and consider the subproblem in this interval here now from 0 to u, and in this interval here from L to 0. And what you then can see that is that if you take a closer look to the separate regions, then you can find tighter relaxations. So for instance, if I do not take now the green inequality here, which was an overestimator on the entire interval L to U, but replace it with the orange overestimator, which is now a valid overestimator in the subinterval from 0 to U, the feasible set that you create are these two green feasible sets of the relaxations. So in this situation, you're getting tighter, and you have the nice property that the red point that we had before, which was the one here, is not part of the union of the two newly constructed relaxations in both subintervals. Okay, so you're getting tighter, your bounds are getting better, and you exclude the old points. This very much sounds already like the wish list that we had for branching in the other setting as well. And what you also see is, if you are not considering polyhedral relaxations, maybe one click back, the green ones here are, of course, polyhedral relaxations. And this is nice because it's automatically a convex relaxation. But if you go to convex relaxations, you, for instance, can exclude what I marked now red here, because on this interval, for instance, the graph itself is a convex function. This is only due to the fact that I restricted it to this new interval. And if I take now the function itself as an inequality and this linear overestimator that I just constructed, I get again a tighter feasible set. Okay, so the question is, how do we construct polyhedral or how do we construct convex relaxations? There is the question in the chat whether it is safe to say that you split the set on the inflection point. No, in this, I mean, I think you mean exactly this point here for x1 is 0. In this example, it worked, but usually it does not work. I will show you an example later on. I will come back to this question when I have the picture for it. Okay. Good. So, of course, we have a to-do list now for the non-convex MINLP setting. So we need to know how to construct polyhedral or even convex relaxations of non-convex constraints. And we have to deal with the question, and this is more or less the question posed in the chat, how do we do this branching? So how do we split the set in at least two subsets? Okay. So we will deal with these questions in the following. And of course, we have to kind of understand what are the assumptions that we have to pose so that also this spatial branching process leads to finite termination or at least convergence of the respective process that we generate. Okay, so we are now going to discuss first what generic relaxation strategies are out there. And for this, I'm going to explain you rather detailed what is really happening in the solvers that you will use or that you will have to use when you try to solve a non-convex MINLP. And the definition here is the one of a factorable function. So we call such a function mapping from Rn to R factorable if it can be written as a sum of products of univariate functions out of a given set that needs to be predefined. And the arguments of these functions out of the predefined set curly O here are either variables, constants, or other factorable functions. Okay, that's super easy in practice to understand, but maybe the definition is a bit general so that it's not yet directly clear. So first of all, what is this curly O? For instance, this might be plus or minus or the multiplication, division, taking the function to some exponent. but also other elementary functions like the sine, the cosine, and whatever you might think of. But not really whatever you might think of, because not all functions are factorable. So maybe the two most important ones in optimization are integrals, for which you simply do not know the antiderivative. Such integrals exist, and if you don't know the antiderivative, you cannot represent it with a finite set of functions. And what you also often have in optimization is that you have kind of black box functions. For instance, that a function evaluation is the result of a simulation run of a black box software package. And of course, then you also do not have such a factorable form because you cannot represent the output with a finite set of elementary functions. The reason why we do all this is that we, for being able to construct these over and under estimators that will lead to our relaxations that we will use, for this we need really the symbolic information about the functions. Without this symbolic information, we have no clue to generate these relaxations. So how is this then organized if you take a look into these codes? So usually these factorable functions, which is, say, the math part of this world, translates to so-called expression trees in the implementation of this math. And an expression tree formally is a rooted tree with constants or variables as leaves and n-array operations at inner nodes. This is, again, a bit complicated maybe, so here's an example. I see the question in the chat. I will finalize this slide and then I will go to the question. So for instance, if you have this function f here, then you can represent this function with this expression tree. It's rooted, the plus node here is the root. And then you can, for instance, have that this plus is this one. So you add x2 to the 3, which is this subtree rooted at this operator, because it's x2 to the 3. And the same you have, for instance, here for this x1 times log of x2 term. Here's the times, so x1 times log of x2, and then you add, so to say, these two subtrees, and then you have the expression tree for this constraint. So now let me, some functions can be only factorable locally. This is true, yes. And I don't think that it's possible to get a non-factorable function as a composition of factorable functions. Because if the composition operator is itself included in the set curly O, you can just plug these two trees together and you get another expression tree. Maybe I'm missing something right now, but to be honest, I never thought about this question before, but I don't think that this is possible. Okay, so what is then a factorable MINLP? So if all the functions that are part of your MINLP, if all of them are factorable, we call the MINLP a factorable optimization problem. And then we can represent the entire optimization problem. This is not an expression tree anymore, but kind of a generalized version of it. And this is then what's called a DAG, so a directed acyclic graph. So how does it look like? Think, for instance, about this optimization problem here. This is a non-convex MINLP. And what you then get is, maybe we take the objective function here. We have x1 plus x2 to the 2. So this part here on the left is the objective function. And you can find every other of these factorable functions in this graph as well. Okay, so for instance, take everything to the left-hand side, then you have -5, which is this one brought to the left-hand side, plus x2 to the 3, which is this guy, plus x1 times x2, which is this one, okay? And of course, this is not a tree anymore because you get an acyclic directed structure, which has in the undirected version of the graph, of course, cycles. But this is what you want to have in practice, because it means that if you have for some parts of your model a convex relaxation, you can automatically reuse it for the other parts of the model that have the same terms, for instance. Okay. And if you have a factorable MINLP, you can reformulate it so that it's all composed out of these atomic functions that are part of your set curly A. So what we do is the following. First of all, we state how our bounds of the variables here explicitly. And we introduce new variables. So for every atomic function, theta k in this curly O, I can take a look in this expression tree, and for the result, I introduce one new variable. So every nonlinear term is replaced by one additionally introduced auxiliary variable. Here, these are q many. So I have this structure that xk is equal to theta k of x. Theta k is in one of my predefined, is in the set of my predefined functions. And then I have from k equals to n plus 1 to n plus q. So I have q many of these terms in my optimization problem. And as a convention, the last variable will always be the objective function. So I also rewrite it as such that the objective function is always replaced with the lastly introduced auxiliary variable. So here's one example. I'm not going to discuss every aspect of this example, but it's the same problem as before, where we had this duck for. And what you now do is you just go over it and replace it term by term. So for instance, the objective function, which is x1 plus x2 squared, this is replaced by x9. So how is x9 defined? x9 is x1 plus x8. x1 is already part of the original function. So what is x8? x8 is then x2 to the 2. Okay. And you can go over this and you can do it for every term. And then you get this representation that every variable is either a linear expression or bounded by lower and upper bounds, or the result of one of these atomic functions out of your set curly O. And the nice thing about this is that you then only need to derive convex relaxations or polyhedral relaxations for these, I call them now atomic functions, okay? These very easy functions that you included in your set curly O. But this means as well that if you have a function in an optimization problem that is not part of this predefined set curly O, the solver cannot handle it. Okay, so if you go to a global solver and you have a square root in your optimization problem, but your global solver in his or her set curly O does not include the atomic function square root, you have to go to a different solver. Okay, but it allows to derive on these atomic functions convex relaxations that can be reused everywhere in the model by only applying the same technique once, but at different places of the model. Okay, one other thing that I'm not going to discuss in detail, I will make too many mistakes if I go into the details here, but what you can do easily, for instance, with such expressions like this one here for x4 is that you can easily do what's called bound tightening, and we will discuss this later on as well. Because, for instance, at the very beginning, you knew that x4 is bound, has no bound. But since you have bounds on maybe the arguments of these atomic functions, and if you know something about the atomic function, then you can bound variables that not have been bounded before. Okay. We will discuss this also a bit later in a bit more detail. Okay, how to use this for bound typing. So what we now want to do, oops, this is the next slide, is we want to consider these non-convex sets which are easier to deal with. So this is just the vector in R to the n plus q now, so in this lifted variable space, with the property that the polyhedral constraints are satisfied, the bound constraints are satisfied, the integrality constraint are satisfied, but that the only nonlinear term is the one that is related with the kth atomic function. So all the other stuff or all the other non-convex things are not included here. In this set, we only consider this one non-convex function, like the sine or like exponential or whatever you might think. And then we have an easier problem when we want to derive relaxations, because we can now ask, what are convex sets theta k bar that are convex relaxation of theta k? And yet you can do it per a per. You can do it for k equals 1 plus n plus 1, n plus 2, and one after the other. And with this, you can also write down the convex relaxation, or better to say, a convex relaxation. This is, of course, not uniquely determined or uniquely defined of your original problem. You just write down everything as it was stated before, but you replace theta k here with theta k bar, so with the convex relaxation. And of course, this is then convex. Okay? That's the idea. And then the remaining question, of course, is how to find theta k bar. So how to find for these atomic functions the respective convex relaxations. So one thing that is very often done in non-convex MINLP solvers is to use polyhedral relaxations. This is, of course, a special case of convex relaxations, not necessarily the tightest one, which means it's not necessarily the one that is giving you the best lower bound, but it's easy to solve because you get a linear model, right? So this is the upside compared to the downside of that the bound is not the tightest possible. So here's again the non-convex black function that we discussed before. And here I also plotted a convex and even polyhedral relaxation. This is just the set that is included in these green polyhedral thing here. And then, as before, you can do via spatial branching, a tightening whenever you solve the polyhedral relaxation, and when it turns out that the solution to this polyhedral relaxation is not feasible for your original problem. But still, I mean, that's a bit, maybe this looks too easy now, because if you look at pictures, it almost feels trivial to draw the best possible polyhedral relaxation. But for a complex function, this is not that easy if you do it out of a figure, okay? And we have to discuss how to do this. Okay, a bit more formal. What do we need? So if we think back here in this non-convex setting where the black graph of the non-convex nonlinear function is the feasible set. What we aim for is a relaxation that is convex. Let's stay in this one-dimensional setting. What we need, of course, is an overestimator, which is a function that is concave. Like, for instance, this piecewise defined function here, that's a concave function, and it's an overestimator. Okay, it's always above the graph of the function that we are originally considering. And for the other part, we need an underestimator, which is convex. So why? Because if we take convex underestimators and concave overestimators, the resulting feasible set, which is then a relaxation, is a convex set. And for convex problems, we know how to solve them to global optimality so that our lower bounds that we get in some subtree of the branch and boundary again are valid. So now let's put this into math. So we have such a function f. This is maybe not a convex function, but it's defined on a convex set. And then we call a function here, it's xi, a convex underestimator of f on this set omega, if, of course, two properties are satisfied. The first one is it's a convex function, otherwise we wouldn't call it a convex underestimator, and it's an underestimator for all the points in the feasible set. Okay, so in other words, a convex underestimator is an underestimator that is convex. Okay, that's not too hard to understand, I guess. And we call the set of all convex underestimators, I mean, there are infinitely many, for the function f on the set omega, this u of f and omega. And of course, you can do the same for concave overestimators, which are concave functions that overestimate the function. And the set of all those concave overestimators is O of f and omega. And then, of course, you want to have not only any or an arbitrary convex underestimator or concave overestimator, but you want the tightest one. And what does this mean? This means that you are looking for the function which is here called vex. Vex of omega and f. And this is simply the supremum, the pointwise supremum over all convex underestimators. And this is called the convex envelope. This is the tightest convex underestimator. And you can do completely the same. You have to take the infimum here in comparison to the supremum here. And then you call the function cave for concave envelope of f on omega. So these functions are the ones that you're aiming for. Yeah, for instance, here you see these two functions. So in those areas where the function is concave, like here or here, the cave function in this area is the function itself. It's the tightest concave overestimator. And here, for instance, in between, you can do nothing better than the polyhedral and thus concave overestimator. And you have the same here, right? Look, in this convex part of the function itself is the convex envelope. But if you leave the convex parts of the function, you get the dashed lines here again, which represent then the best possible convex underestimator, so the vex function. Good. An alternative definition, if you want so, is that the vex function is the one that minimizes the error in the max norm between the function and the set of functions which are convex underestimators. So they solve this optimization problem. And the reason simply is that the pointwise supremum of convex functions, again, are convex functions. This is why this works. Okay. And of course, you can do it the exact analog for concave functions as well. Good. And then maybe you can remember back to this convex hull argument of mixed integer linear optimization that I made at the very beginning of the lectures today. There is an analog theorem, and here it is. So if you have a compact feasible set and a continuous function, and you want to solve this minimization problem, this is the same as what you get when you minimize your x over the convex hull of omega, and if you do not take f, but vex of omega and f. So this optimization problem here on the right-hand side is a convex optimization problem. That's easy in the sense of complexity theory. Thus, since this is the same, this means that finding these convex hulls and finding these vex functions needs to be as hard as solving the original optimization problem. So if you have an oracle that just gives you the convex hulls and the vex functions, you're done. But then all the complexity of your non-convex problem is kind of hidden in this oracle. And there's a second part of the theorem that's telling you that if you take the set of all global optima of this left-hand side and of this right-hand side, the one is M and the other one is N, if you take the convex hull of the set of all global optimal solutions here of the left-hand side, you get the set of all global optimal solutions on the right-hand side. So this is kind of the analog of what I showed you with these convex hull and separation arguments at the very beginning when we discussed mixed integer linear programs. Okay, so the problem with these relaxations of non-convexities is, I guess, best described with the first sentence in the book Anna Karenina by Leo Tolstoy, which is, you might know it, all happy families are alike, but each unhappy family is unhappy in its own way. Translated to math, this means that whenever you have linearities, they are all the same, but non-linearities, they all are different in their own way. And that's kind of the good and the bad thing with these non-convex relaxations, because you have to deal with all of them separately because they are all kind of different. They are like the unhappy families in Tolstoy's book. But on the other hand, this also means that there will be one left for you if you want to do it. Yeah. So what you find in the literature, this is just an arbitrary example here, is that people write a paper, and this is a well-published paper by Leo Liberti and Pantelidis, that they just tackled relaxations of the non-convexity of the type that you get if you consider monomials of odd degree, which is, you might agree with me, a rather special case. Okay, but I think this is a paper published in the Journal of Global Optimization, so it's a nice paper. Okay, but you have to do it non-linearity after non-linearity. So this is also clear then that I cannot show you everything, but I will show you some examples. So the first one are the so-called alpha underestimators, which have been published by Androulakis and co-authors and Maranas and Fludas in the middle of the 90s. So assume you have a function f, it's twice continuously differentiable. I will tell you in a minute why. And it's a general non-convex function. How can we find a convex underestimator? So first of all, we have to deal here for being able to do something, the domain needs to be specified. And here we just take the box, okay? The domain of this function in Rn should be just the box that I get as the cross product of intervals for the separate components of the function or of the arguments of the function. Well, and then I define this phi of alpha of x function, which is just the sum over all components of my argument. And then I have alpha I, and then I have the lower bound minus the variable times the upper bound minus the variable. It will become clear in a minute why we do so. And then I consider the following function. It's this f hat the wrong way around. I don't know how this is f check. I think people call it check. So this is f check. And we define f check to be f plus this phi alpha of x function. If I write this out, this is f check. Okay, so here it is again. And the first thing that you can see is That's an underestimator. The reason is that this phi alpha of x term here is always non-positive. Because this guy here is always non-negative, but this one is always non-positive, so it will stay non-positive. Okay? At least if alpha is non-negative as well, which we assume. So we have an underestimator, but now the question is, of course, what about convexity? We need a convex underestimator. And for this, we have to choose the components alpha I of this non-negative vector alpha in an appropriate way. How do we do it? The next lemma here is telling us on how to do it. So here's the lemma again. So if we take our function f on omega, and if we take the Hessian matrix, it has eigenvalues. Take the smallest one. This is lambda min. If I now define alpha I so that this inequality holds, lambda min plus 2 times the minimum over all the components that I have in my alpha vector, if this is non-negative, then f check is convex. And since I already know that it's an underestimator, I have shown that this is a convex underestimator. Okay, so how do we find out whether a function is convex? We take the Hessian matrix and take a look whether all eigenvalues are non-negative or whether the quadratic form is non-negative everywhere. So this is the Hessian matrix. It's the Hessian matrix of the original function plus 2 times the diagonal matrix that has alpha as the vector on the diagonal. Okay, just take the second derivative of this function here, and you see that this holds true. So what we now need to show is that this Hessian matrix here, H of f check of alpha of x, is positive semi-definite. And this is the definition of a matrix being positive semi-definite. We just take for all possible vectors H in Rn this quadratic form, and it needs to be non-negative. Okay, so let's write this down again. This is what we had. And now we take with this matrix, indeed, the quadratic form. It's linear, so I can split it. So this is H transpose HF of x times H plus 2 times H transpose the diagonal matrix with alpha on the diagonal times H. This is just the definition. And then I know that since H of f has a minimum eigenvalue, which is lambda min, I get for this term by standard linear algebra, this estimation. And of course, I get the estimation for the second term if I don't use all the alphas on the diagonal, but if I replace it everywhere with the minimum one. That's the second one here. So now you can factor out the 2 norm squared of H, which is non-negative because it's a norm to the 2. And then we have that lambda min times 2 times the minimum of all alpha E needs to be non-negative. This is our assumption, and this is why it's convex. So this is one example that I showed you now, where you see how you can derive convex underestimators of general functions. But that's not easy, right? I mean, you have to compute the minimum eigenvalues. If X is a large dimensional vector, this might take a while, okay? So this is not as easy as it might look at the first glance. So are there easier situations? Yes. Maybe the most famous convex under and concave overestimators are those by McCormick. These are the so-called McCormick inequalities. And this is about the bilinearity x times y that we discussed at the very beginning. So the main lemma why this paper that I just showed you is so important in the literature is that you have this bilinear constraint, and if you have bounds on your X and Y variables that are part of this bilinearity, then these four inequalities, these are the so-called McCormick inequalities, then they are all valid. And it's super easy to prove. So take, for instance, for the first inequality, the product X minus its lower bound times Y minus its lower bound. Since it's the lower bound, we know that these two are non-negative, so the product is non-negative as well. Just multiply it and take all the stuff that is not X times Y, which is, by the way, W, on the other side, and you get this inequality. Super easy. But what's nice is that for general bilinearities, this is the best that you can do if you want to do it with a polyhedral outer approximation, right? So these are all polyhedral constraints. It's all linear. And I mean, here's just a year ago, I guess I took this screenshot. That's the paper in Google Scholar. You see, it has more than 1,600 citations, and that's just because this very simple idea is so useful for non-convex optimization, because of course bilinearities appear at very, very many places in optimization models. So this is why this is used so much. Okay, so these were two examples. As I showed you or explained to you before, it's like that you have to deal with every non-linearity after every other non-linearity. So there's a huge literature, and I of course can give examples here in the time frame that I have. So there's the question in the chat on how to apply those ideas to a non-linear family of curves. So I'm not sure whether I understand what a non-linear family of curves is. I mean, how do you apply this in general? So think about that you have multiplication in your set curly O. This means that one of these theta k functions is the multiplication. And for this, we wanted to find a polyhedral and convex relaxation. So for this multiplication operator in your curly O set, you just apply what I just showed, these four inequalities. And then, of course, you still make a mistake, that's for sure. But then you can do spatial branching, which we discuss in a bit more detail next, to tighten these relaxations. So since it's not that long ago that we discussed the branch and bound for the MILP case, I think I can skip these slides. This is what we discussed before. So here's now again the setting with a non-convex MINLP. So as before, what we need to know is how to compute lower bounds on the optimal objective function value of the subproblem. The subproblem always is one node in the branch and bound tree. And it's always specified such a node via the original problem plus some additionally imposed bounds that we derived via branching. Okay, there's another question. McCormick inequalities require the addition of one variable per bilinearity, but what if we have something like x1 times x2 times and so on times xn? The easy way is just apply it iteratively. Replace x1 times x2 with omega. The next thing that you then replace is omega times x3. Let's call that z. And then you replace z times x4 is something else. So you can simply do this in an iterative fashion. Okay, so back to this one here. We have to find these relaxations of these subproblems, which are the nodes, and these should give us lower bounds. This is the bounding step again in branch and bound, and we need the procedure for partitioning the feasible set, which is the branching, okay? And this both we have to discuss a bit more in detail. So this is the original MINLP plus some further imposed bounds. So with these LU, which are the bounds here, this specifies one node in my branch and boundary. Okay, so this is what we want to consider, and this is what we want to compute lower bounds for. So this is the goal. How do I get a convex relaxation so that the lower bound is as tight as possible? So what we can easily do is take just the polyhedral relaxation. Just think back to McCormick for a theta k that is the product of two variables. Then McCormick would lead to this polyhedral relaxation, which is then the LP of L and U. And these polyhedral constraints then represent, for instance, the four constraints of the McCormick inequalities. So now assume that this has an optimal solution, which we call X hat. So then we have two situations, two possible situations. The first one is that this X hat, which is the solution of my LP relaxation, is feasible for my original problem. This is again the lucky shot situation, okay? So in this case, we know that we solved the relaxation, but the solution is feasible for the original MINLP. So we solved the original MINLP at that subnode, so we can cut it off. We can prune this subtree. That's more or less the same idea as with the classic branch and bound that we discussed this morning. On the other hand, this is situation number two, and this is the much more likely one, is that your LP solution X hat is infeasible for your original problem. And now we can have two reasons for this. The first one is the reason that you already know from mixed integer linear programming, which is that you simply have a variable index, I in capital I, so that xi is still fractional. So you're not yet integer feasible. And then you can do a branching on these integer variables as you know it from the classic mixed integer linear optimization setting already. The other situation is that you maybe are integer feasible, but that you are not on your original non-convex feasible set. So in this factorable form already expressed, this means that there is an index from n+1 to n+q such that x hat k is not equal to theta k of x hat. And then we have to do a branching on a continuous variable to tighten the, for instance, polyhedral or in general convex relaxation of our nonlinearity. And this is what's called spatial branching. Good. So how to do it? So think about the situation in which xi is one of the arguments of this function theta k, which is not feasible for the point that is the solution of our LP relaxation. One possible way, and this is now related to the branching question at the beginning of this afternoon session, is that you could say, well, I just split at the current solution. But that's a bit tricky because, first of all, the two resulting feasible sets, they are not disjoint. Remember, this is always disjoint if you branch on integer variables, right? You round down, you round up, so it's disjoint. That's not the case if you do it as here. And even worse, or maybe one other thing first, a further difference is that you don't have to do this at all for convex MINLPs or purely integer non-convex MINLPs. there you only need to branch on integer variables. But, and in these cases, the finiteness of the number of integer variables gives us finite termination, right? So this is what we cannot apply anymore to guarantee the convergence or the finite termination of our method. So maybe one other thing. What's even worse than that the two sets are not disjoint is that the old solution, which was infeasible, is if we do this branching, still feasible for both of the created subproblems. Okay, that's a remarkable difference. Okay, so what do we do? Assume that this omega of L and U is the feasible set that I have for my node problem that is specified with L and U. So what we now have to do is we have to split this into two subproblems, which also corresponds to two feasible sets here. This F here should be an omega as well. So this both should stand for the feasible set. And now I'm not able to show you the entire theory because this would be an entire lecture series on global optimization. I only want to give you the main concepts here. So in global optimization, and this is what we do now, we call a bounding operation in this setting an operation that yields two new subproblems, like you know it from standard classic branch and bound, so that you get for both problems lower bounds and upper bounds. Okay, you split your problem, you have a lower bound and you have an upper bound. So this is a bounding operation if this holds true. And then we call such a bounding operation consistent if at every step in our method, these subsets of the feasible set of the last problem of the parent node can either be pruned, for instance, due to infeasibility, or can be refined in a way that you have a finite sequence of such further and further splitted sets that are the outcome of your bounding operation, so that the upper and the lower bound converge. If this happens, this is the right assumption for being able to prove that you will converge. And even more, if you assume that all of these sequences of successively refined partitions of the original feasible set is indeed finite, then we call this bounding operation finitely consistent. For instance, if you only branch on mixed integer or only branch on integer variables, this is a finitely consistent bounding operation. If this is the case, then there is this famous theorem by McCormick, and you can also find maybe a bit more modern version of the theorem and of the proof in the book by Horst and Thuy. By the way, Horst was also a Trier mathematician sitting in this office here while writing this book. And the theorem states the following: if the bounding operation that you use in your algorithm is finitely consistent, then you will terminate after a finite number of steps. But if you have general non-convexities for which you have to do spatial branching, you're not finitely consistent, because independent of how many branching steps you do, you usually get a relaxation in which you can make an error. And this means that in general, you also will have a gap between the upper bound of a solution and the lower bound of a solution. And then we cannot talk about anymore about finite termination for non-convex problems, but only about convergence. Or if we have this convergence setting, that we have finite termination only if we stop with a solution that is only epsilon feasible. That is, we have to allow ourselves some error in the feasibility and in the optimality of what we get in the very end. That's the main difference. If you do not have this finitely consistent bounding operation, which you in general not have, in finite time, you can only get approximate solutions. This was not the case before when we talked about, for instance, convex MINLP or even mixed integer linear programming. Okay. That's why it's so much harder. That's the difference. So still the question is how to do spatial branching. We have not yet discussed this. So branching, of course, means that you split your problem in at least 2 problems. It can be more than 2, by the way. Nobody told us that we are forced to always use a branching of 2. We can also have a branching of H, but we have to have at least 2. And of course, we want to have the branching set up such that the lower bounds that I get for my newly created subproblems, that they should be no smaller than the lower bound for the original problem. So the lower bounds should, of course, increase. Otherwise, I will not make any progress. So let's stay with the setting that we always have the situation that we create 2 new problems, okay, as before. And most implementations do this via variable branching. So if you have a variable xi that you want to branch or that you have to branch on, because this is, for instance, in part, this is an argument of a function theta k, which is not satisfied in your LP relaxation at the node that you're considering. Then you, for instance, can define a value b and say, okay, in one problem, I have the inequality constraint xi is not larger than b, and here xi is not less than b. But again, we did not yet have answered the question because nobody told us on how to choose I, and nobody told us up to now how to choose b. And by the way, this was trivial to answer for instance, binary branching in mixed integer binary optimization, right? Okay. So, of course, this is what I already told you. If you have a fractional integer variable, that's an obvious candidate, do it. So that's not the interesting case. Yeah. So let's assume that all the integer variables are already integer valued so that we still only need to branch on those continuous variables that are part of such a violated atomic functions. So the nice to haves for a branching rule are these 2 mainly. You want to split your feasible set such that the feasible sets are reduced as much as possible and that your lower bounds are increased as much as possible. Okay, so still, what is a branching candidate? So for instance, it's a branching candidate whenever it's not yet fixed. Of course, if it's already fixed, there's nothing left to branch on. And if it's such an argument of a function that is violated. So one specific example to make this very clear, think of theta k as the bilinearity xi times xj, and xk is the argument. And assume that the LP relaxation, which got the hat, does not satisfy the non-convexity. And assume that, for instance, xa here, this variable, has still a lower bound that is strictly smaller than its upper bound. So it's not yet fixed. Then branch on it. This gives you a branching candidate. Okay, this is what I already told you. And then still, this is the same situation here. Then still the question is on how to choose B. Okay, and that's not that easy. So I will not answer this question completely. But for instance, if you got this solution here, this is the hatted solution. You can, for instance, take this B, which is, by the way, not xi hat, it's something different. And you obtain the property that this point here, which was the relaxation solution before, is not part of the feasible set of the two new subproblems, which is then the smaller gray areas here compared to the larger gray area here. Okay. Okay. So here you see in this picture, yeah, and I mean in this picture here, that you have much more degree of freedom to decide on how to set up, for instance, here this scalar B, that is to define where you want to branch. Okay, and this also depends on the specific function theta, which is violated right now at the moment. So this belongs to the treatment of this atomic function to clarify on how to set this B, for instance, if you have a function where it fits here in the scalar world. Okay. By the way, this is what I showed you before. Just taking the solution and branch at the solution does not need to work, because this does not need to exclude the old solution from both feasible sets. Okay, so the naive way of saying, well, just take the solution and split there, does not need to work. Okay, so since this is again very function specific, I'm not going into the details here. I mean, there is a lot of literature a lot of papers in the literature on global optimization where you can try to read about these things. Okay, there's one more question in the chat. Ah, no, it's okay, thanks. Okay, perfect. No more question. Whenever you have a question, just let me know. So the last thing that I want to discuss with you is bound tightening. But maybe before we start with bound tightening, the main difference, again, let me stress this. The main difference is that whenever you have to deal with spatial branching, that is with the branching on continuous variables, you have to consider every nonlinearity on its own. You have to derive convex relaxations, maybe polyhedral relaxations. You have to set up branching rules that are well performing for this specific nonlinearity. And there is no one fits it all approach. Okay. This is the interpretation of this Anna Karenina starting sentence here in this world of non-convex MINLP. Okay, so finally, bound tightening. So what is bound tightening? Here are the main motivations for it. I mean, all the pictures that I showed you made clear that the performance of these solvers, of course, strongly depends on how tight your relaxations are. The less error you maybe make and the less spatial branching steps you maybe need to make before you satisfy a prescribed tolerance of, say, epsilon in feasibility. And what's also clear, I guess, from the figures is that the tighter the variable bounds are, that are the bounds for the variables that are the arguments of the function that you are considering, the tighter usually also the convex relaxations will be. That's why many MINLP solvers spend a lot of time in so-called bound tightening. That means tightening the bounds of all the variables of your problem as much as they can, because this will give you later on much tighter convex relaxations and thus a better performing algorithm. Excuse me. So what is bound tightening? So this is the feasible set that I showed you before of the original MINLP. Okay. So now think about a point x hat, which is feasible and which has the objective function value z hat. The easiest way, not the easiest, but the most naive way of doing bound tightening is to say, well, I can just for every variable solve two optimization problems. One in which I minimize the variable over the feasible set and the constraint that the objective function should not be larger than the known objective function value z hat here. This, of course, gives you maybe a tight lower bound, which is larger. This is why I call it tight, which is a larger lower bound compared to the original one. And of course, you can do the same with the maximization problem here to get maybe a tighter upper bound. But the problem with this, of course, is these problems that I wrote down here, they most likely are as hard to solve as the original problem. So it's not clear whether I really gain something. So what else can we do? So what you often do is that you try to produce for one variable a tighter bound by using already tightened bound for another variable. So let's make this maybe clearer here in an example. So assume you have the atomic function to the 3. So here you have xj is xi to the 3. And assume that somebody told you, hey, li and ui are tight bounds of xi, the argument of this function. This means that you can, of course, tighten the bounds on xj by just intersecting the old bounds that you know on xj with the bounds li to the 3 and ui to the 3, which is correct, by the way, since this xi is a monotonic function. So xi to the 3 is a monotonic function. Okay. And this you can do with very many other problem ingredients or constraints as well. So for instance, consider you have such an affine linear constraint here. Then you can say, well, these coefficients aj here, you can split them into those that are positive and into those that are negative. And if you then want, for instance, if you want to derive a lower bound on xk, you just take this sum here, and for all those aj that are negative, you take the upper bound, and all those aj which are positive, you take the lower bound. I mean, of course, you get a lower bound on xk. And if you just flip the roles here in the sums, you get an upper bound. Okay? And this you can do for very many things. Okay? So, and you can also iterate this. If you have now for xk a new bound, you can maybe use this information to get for another variable better bounds. Okay, so you can iterate this through the DAG, the directed acyclic graph that you have for your problem. Okay, if you do it like this, this is called bound propagation. You go through your DAG and you try for every part of the DAG to infer better bounds, and these better bounds you use somewhere else, and this you propagate through your DAG. And I mean, this may converge, then you know you have the tightest bounds, but there are some theoretical papers. I remember one by Leo Liberti and co-authors who analyzed this fixed point mapping, which stands behind, but in general, this does not need to converge. Okay, but this is what's called feasibility-based bound tightening, because you take only feasibility ingredients. You can take variable bounds and you take constraints. And putting those two things together, by doing so, you try to infer tighter bounds. So this is why it's called feasibility-based bound tightening. You can also do optimality-based bound tightening, which is more or less what I just showed you here. Okay, because here you also do not use only the, why can't I mark this? You cannot only use here the feasibility, x is in omega, but also information on the objective function value. If you do it like this, this might give you better bounds. And this is then called optimality-based bound tightening. But again, as I told you before, usually these two problems are as hard as the original problem was. So what people then do, for instance, in the codes that you can use is that you do not use, for instance, omega here or this nonlinearity f, but that you also, for the optimality-based bound tightening, you replace these feasible sets by, for instance, polyhedral relaxations. This still gives you valid bounds, right? If you minimize for the lower bound, and if you do it with a relaxation, that's a valid lower bound. Same for the upper bound. But of course, the bounds get weaker. They are maybe not as tight anymore as before. And this still might be an MILP to be solved. So this still might be expensive. Okay. So for all these bound tightening techniques, it's the case that you very much have to deal with a compromise between what are you willing to invest in terms of computation time for getting at the very beginning, or maybe also in the intermediate process of solving the problem, tighter bounds, compared to what you gain or maybe lose if you have better or worse relaxations. Okay, and to find a good compromise is often one of the key, I would say, commercial secrets of those non-convex solvers that are the best that you can find out there. Okay, so maybe a bit about modeling languages. So this is now the very practical part, and I will be rather fast here. So if you have maybe in your PhD project an MINLP that you need to solve, the question always is, how do I tell it my computer, right? So, and for this, you have these modeling languages that provide both the possibility to write down the model in a computer language, and they usually also provide you interfaces to solvers so that you can directly solve the problem. So the very two classics here are AMPL and GAMS. Okay, they are rather old, both, but still heavily used in the MINLP community. And with those, you can write down optimization problems that are MINLPs, also non-convex MINLPs. And they also have these interfaces to solvers so that you can afterward, if you implemented the model, say to a solver, please solve it. Okay. What you can also do is, and here I'm going to go into a bit more detail, how can you do this in a more specific way if you want to, for instance, use Python, and if you want to give your Python model to Gurobi, which is the solver which today can also solve non-convex problems. And this we will also maybe need in the exercises that you have in the last afternoon session. So what I will now do, I will switch here to my editor. So now you should see my editor screen, and this is just Python code that you see. If you do not see my editor, please just let me know. Yeah. And what you then do to implement such a model, for instance, is that usually, for instance, here, if you use Gurobi, they have a Python interface that you need to import here. And then you create at the very beginning an empty model. An empty model is a model that does not contain variables or constraints or an objective function. This is what you usually start with. Okay. This here is just there to define some problem parameters. This is just random stuff. It's not important, but I have to do it. Otherwise I won't get a complete model. So after this one here, so this model class from which I call, for those of you who know what I'm talking about, from which I call the constructor here, generates an empty model. The first thing that I then do is I say whether I want to minimize or maximize. This is the sense of the model. Maximizing, which I'm going to do here, is encoded with the -1. And then I now build all the variables and all the constraints of the problem. So the first thing is that for every index from 1 to n, I have a variable that I add here. So this is add var is one of the functionalities that you get in this Gurobi Pi interface. And it adds a variable to the model, which is called model here. So it's rather easy to read and write, I would say. And you can give these variables names, and you, for instance, can give them already directly, for instance, here, objective function coefficients. This is values at the array index IDX, and the values is what I set up here, but the details here are not that important. Okay, so this is how you get a variable into your model. And if you, for instance, have a constraint, if it's a linear constraint, you can set up something which is called in this Gurobi Pi interface a linear expression, this linexpr here. And then you can just add up in this line coefficient times variable. Then in the next iteration of the for loop, coefficient times variable. So this is something like C transpose X, right? A linear expression. And then you can add a constraint like add var. Now you use add constr for add constraint. And then you, for instance, just give the linear expression, and then you need the right-hand side and the relation. The relation you can easily do with equal, or less than or equal, or larger than or equal. And you need the right-hand side, excuse me, which is the capacity which I defined above here. So then sometimes you have to register all these changes to the model, and then you can just say, Gurobi, please optimize it. Okay. And if you, for instance, go, let me now change to my shell here. If I, for instance, then just call this Python code here with Python so that it's getting interpreted, then Python will call Gurobi to solve this problem. You see, I get an optimal objective function value. It was very fast, so this problem was not a hard problem, yeah, and it gives you some statistics here, etc. pp. Okay, so if you want to, for instance, solve the or an optimization problem with Gurobi and Python, this is how you can do it. Okay, we will give you all these information so that you don't have to remind everything out of your heart afterward. Okay. So there is also the possibility for more general nonlinear optimization problems to use, for instance, in Python, Pyomo, which is also a rather modern modeling language, but I will skip this here. So you don't need to use it in the exercise classes, and you will all get these slides. So here's some kind of tutorial for Pyomo and how you use it. And here's also a certain list of solvers at the very end that you can use. For instance, here's a list of non-convex MINLP solvers. They are always in alphabetical order because I didn't want to put any emphasis on some of these solvers. And I don't want to rate them, kind of. I just want to give you a list that you have a starting point if you have to solve such a problem. Here for convex MINLP, for MIQP problems, if you have something like that, that your objective function is quadratic and you only have polyhedral constants. There is also the NEOS server that you can use if you do not have any solvers at all. You can register there and just send your optimization problems to a web interface, and then I guess you will get an email if it's solved with a solution, etc. So this is also something. You have the URL in these slides if you want to take a closer look. This is just there because I want to let you know, but I don't want to talk too much about it here at that moment, because I mean, there's also no theoretical interest in, of course, a web interface, but it's a very nice service to the community because people who are not able to buy expensive solvers, for instance, still can solve challenging optimization problems on their server. Okay, and then maybe for the 2 last minutes, what else is out there? Yeah, I mean, I now talked to you almost 5 hours about mixed integer nonlinear optimization, and I hope very much that you at least got an insight on a rough meta level, what's happening in the field, what are the main modeling techniques that we discussed a bit at the beginning, and that you know what are the main solution techniques that are out there, and why are problems, for instance, the non-convex ones, much harder compared to the convex ones, okay? I hope that I could give you some insight on this, but of course, in 5 hours, it's not possible to discuss every detail in detail. And a lot of things I didn't touch at all, okay? And for instance, regarding problem classes, these mixed integer quadratic programming problems are very important for practice, and I didn't talk about it. There are the so-called second order cone problems, which are very much on vogue right now in the MINLP community. I didn't talk about it just due to time reasons. It's like that you allow for some very specific convex constraints, but they appear very often in practical applications, and you can do very strong algorithmic techniques with them. So this is why they are that interesting. I did not talk at all about polynomial optimization problems, to be honest, because I do not know much about it. There are other experts on this, but it's also a huge field and very many people deal with it. I also touched very few algorithms that are out there. So I did not give you any specific insight in generalized Benders decomposition, which is used a lot in practice. I did not discuss the extended cutting plane method with you. I only told you that all these bound tightening techniques, primal heuristics, node selection, branching rules, pre-solve techniques, that this is super important for the overall practical performance of an algorithm, but I didn't discuss with you what's out there. So if you want to dive deeper into this field, just go for these topics and there you will find a lot. I only showed you a few valid inequalities. Yeah, for instance, the McCormick ones, for instance, the outer approximation cuts or the Kelly cuts, which are valid inequalities, but there are completely different fields like reformulation linearization techniques, which is an entire field, or intersection cuts invented by Balázs a long time ago, or perspective cuts, which are very important right now in theory and practice. So if you want to dive deeper, take these buzzwords to Google and you will find papers and tutorials and survey articles on that. And of course, there are completely different problem classes that I did not touch. Yeah, I did not talk at all about problems that have differential equations in the constraints. These are optimal control problems. I didn't talk about optimization, MINLP optimization under uncertainty. Let it be in the sense of stochastic optimization or in the robust setting. I didn't talk about optimization, mixed integer optimization with black box functions. And today, I didn't talk about bilevel optimization problems, but you will have some information on bilevel optimization tomorrow. So there we will also discuss mixed integer bilevel problems. So it will fit kind of to what we did today. Okay, I will not go over all the literature here. It's just to let you know that these slides are also something like a source, or meant as a source for you, where you have some papers that you can use to dive into this field. And I only want to maybe point out one specific survey article, and this is the one by Pietro Bellotti and Sven Leifer and Jeffrey Linderoth and many others. It's just called Mixed Integer Nonlinear Optimization from 2013. And that's mainly the survey article that I also used as a basis for this course. Okay, so whenever you think, these slides are not the best ones from time to time, and I do not understand what's meant, just go to this survey and you find more detailed information there on the topics that I discussed here. And there are some other things, the original papers, for instance, here by Land and Doig and by Kelly. If you want to dive deeper into non-convex optimization, go for the book by Horst and Tui on global optimization. This is very thick and with very many information. You can have an entire lecture series about that. This is a very good source, for instance, for non-convex optimization. And then the other original papers, for instance, that I mentioned as well. Well, And that's it. With this, I'm done, almost on time with the topics that I wanted to discuss with you. Whenever you have any questions, just feel free to ask them. There is also this Gather Town meeting that we will have later on as well, where you can just approach me and ask, or you can send something here in the chat, or you can send an email or approach me wherever you want. Okay? Good. Then thanks for listening. I hope that this was time well spent for you. And we will then meet again for the exercise class, I guess, at 4:15. Okay. So from that moment on, Yasmin will mainly take over, but I can give you maybe some information on how we are going to do it. You get the information where you find data and some exercises that you can work on, and we will create some breakout rooms here in this Zoom meeting with at a maximum 5 people per room, and you will be automatically put into one room. Okay, it's not that you will necessarily end up with your best friend in the same breakout room where you can discuss the math, which is on the exercise, which is there on the sheet for the exercise class. But you can then, in a group of 5, for instance, at a max, work on that. And Yasmin and I will try to hop from breakout room to breakout room to give you some coaching and maybe some help while you work on these exercise classes. Okay. We will arrange this now in the meantime, and hopefully we'll have this done before 4:15, but I'm rather optimistic that we can set this up. And yeah, thank you again for your attention, and see you later. Bye-bye. So, sind das jetzt noch, are these questions in the chat, or is this general comments? Let me see. Yeah, so you're all welcome. Thanks. So Yasmin, I will also mute myself and get something cold to drink, and we'll be back in 10 minutes or something like that. Okay. All right. Zacharia or Ibrahim, are you still there? Ah, yeah.
Yeah, we are here.
Maybe you can stop the
the
recording. Yeah. And we also do